Hello everyone, I am Reza Fathi from University of Houston and I am presenting our efficient distributed algorithms for the k-nearest neighbor problem. We call it KNN in short. The problem is that given a set of n data points and a query point q, our goal is to find k points in the set that are nearest to the query point q. It's a well-studied problem in machine learning with multiple applications such as classification. And our goal is to design efficient distributed algorithms motivated by big data where your input data is large and you want to use multiple machines to efficiently process them, or you have privacy concerns such as you have data of patients from multiple hospitals and you don't want to bring all of them in a single machine to process them. So we studied the problem in the k-machine model where your data is distributed over k-machines, and those k-machines are pairwise interconnected. And from now on, in order to avoid the confusion between k-machines and k-nearest neighbors, we will call it L-nearest neighbors. Our algorithm proceeds in rounds. In its rounds, each machine does its local computation. Then it extends message with all of its neighbors. And the size of the message is limited by order of log n bits. And in each round, when we are exchanging the data, we send the distance of data to the query point instead of sending the original data. Because the data can be from high dimensional and it can be very expensive to exchange the data. And our goal is, of course, to reduce the number of communication rounds to get the result. Our result is that we introduced a randomized distributed algorithm in the k-machine model that runs in order of log L communication rounds, and it succeeds with high probability, regardless of the number of the machines. And our bounds are essentially the best possible for the comparison-based algorithms, and this is because there's a lower bound of log L for communication rounds for finding the median of two n elements when they are distributed over two processes, and you are just allowed to exchange one element per round. So indeed, our the L nearest neighbor problem boils down to selection problem that you get the query point, and then you can compute the distance of each point from the query point and put it, say it's in the set of S. And you want to find, if you sort them, you want to find the L's smallest value in the set of S and say DL, and then you can ask each machine to compute the data corresponding to the distances that are less than DL, and then you are done. So how the distributed selection algorithm runs, each machine can compute the L nearest neighbor from the queue. So your state spaces, your search spaces KL indeed. And then if you run the selection algorithm, you can get the result in log of your search space, that is log of KL. How it happens, the leader machine look at the size of the data a machine holds right now. And it picks one of the machines based on the size of the data it holds based on all the data currently there is in the search space, and that machine picks one of its data by uniformly at random and sends it to other machines, and all the machines divide their data compared to that pivot value, that the size of the data that are less than the pivot value and the data that are bigger than the pivot value. And looking at the size of the set in each side, it decides to pick one of them and throw away the other one. And if you continue, you can find the L's smallest value in log of search space, because you are reducing the search space by a constant factor. So here you will get log of KL rounds. And the question is that, can we do faster? And our answer is that yes, we can do faster. By sampling, we can reduce it to a log L round. In our algorithm, indeed, we are using the sampling to reduce the search space from order of KL to order of L. So each machine samples 12 log L points from its set of points and send it to the leader machine. Leader machine collects all of the data that becomes 12k log L sorted, and it picks the data in the 21 log L index of those sorted data, and it sends it to the all machines. The machines throw away the data that they have, and it is larger than that pivot value of R. And then we showed that then the search space reduces from KL to L. And then you have the L, and you run the selection algorithm on that. So your search space is L, and your selection algorithm succeeds in log L because your space is L, and then you're done. We did an experiment to show our algorithms run faster compared to the simple algorithms, where that the leader collects KL nearest neighbor from all other machines, and it locally computes the L's nearest neighbor among those data. And we divided its runtime to our algorithm's runtime, and we show that our algorithms do best when you even increase the size of the L, or you increase the number of the machines. And in both cases, our algorithm runs faster. In conclusion, we introduced an efficient distributed algorithm which runs in order of k rounds, or order of log k rounds. Our algorithm uses a small number of messages and in total it uses only k log k messages, indeed efficient in even messages. And our bounds are essentially the best possible for comparison-based algorithms. And our algorithm can be used as a subroutine for many other problems. And thank you for your attention.